I've got your TA Indiana with me here today for this inclined manometer video. We've got 4 goals. First, what's the purpose of an inclined manometer at all? Second, we're going to find the initial pressure in this tank at the beginning of the problem. Third, we'll go ahead and solve for the final height of liquid in the inclined manometer after we change the pressure in the tank. And number 4 will be a mystery goal. You'll find out at the end. So the purpose of an inclined manometer is to increase the resolution of the scale so that you can get a more accurate measurement. In chemistry, this would be the difference between a beaker and a graduated cylinder. Beakers are just used for mixing and pouring because you have very few numbers on the sides. You can't really tell exactly how much you have. A graduated cylinder, though, is much thinner with many more lines of measurement so that you can read exactly how high they're filled. And you can read them much more accurately because they're so much thinner and taller. So consider this beaker that has some amount of fluid. All you can really tell is that it's somewhere between 50 and 100, maybe at like 60. But then if you take that same volume of water and put it inside a graduated cylinder, the same short, fat volume of water in a beaker will turn into a tall, thin volume of water in a grad cylinder, and you can get a much more accurate reading. Here we go, about 63 milliliters this time. Now the change from a U-tube manometer to an inclined manometer is very similar, but with one key difference. When going from a beaker to a graduated cylinder, you use the same volume of water in both containers. But in manometers, it's actually the height that will be the same. In fluid systems, pressure will be the same at the same depth. So both a vertical U-tube manometer and an angled inclined manometer will be at the same height. Even if this requires moving a different volume of water, there's going to be more volume of water in the inclined tube manometer, but they'll both be at the same height. So looking at these 2 examples, a vertical U-tube manometer is going to have each line very close together. But over on the inclined manometer, each line is drawn at the same height increment, but you can see visually they're much further apart because they have this additional horizontal separation between them. And just like graduated cylinders, this makes it much easier to read the scale. And that's it. That's the purpose of an inclined manometer, is just to have a scale that is more drawn out to make it easier to read. And with that, we've got to take a quick break because as you can see, Indy wants to play. He will not run on his wheel by himself. He has to have me there. It's just like a little kid like, "Mom, watch me jump on the diving board." Same thing. All right, so we've got a pressurized tank on the left-hand side, and note that the top is not open to atmosphere. It's just connected to some other pressurized system. And then an inclined manometer on the right-hand side. So given that there's an initial 2 centimeter gap, let's find the initial pressure within the tank. Then, if we consider a later time, once the manometer height has changed to an angled distance of 40 centimeters, find the new pressure in the tank. And then third, for comparison, we'll actually figure out what would the vertical height difference be if this were just a regular U-tube manometer. So to find the initial pressure in the tank, I'm going to use the hydrostatic equilibrium equation, also called the manometer equation. I'm going to start with the known pressure on the right-hand side, which is atmospheric pressure, 101.3 kPa. And since the level of water inside the tank is above the level of water inside the manometer, it's going to be at a lower pressure. So I take the atmospheric pressure and then subtract rho GH, density times gravity times height. So I'm making an assumption for this problem that the density of water is 1,000 kilograms per meters cubed, but if you were given temperature, you could get a more exact number by looking it up in a table. 9.81 meters per second squared for gravity, not 32.2, which is for English units, and then a height of 2 centimeters. Now this equation shows the importance of writing down units, because we're going to need multiple unit conversions to make this work out. So since a Newton is a kilogram meter per second squared, now we're in units that actually work. So a little bit of calculator work and we get an absolute pressure of 101.1 kPa. Or if we wanted a gauge pressure, which is just the difference between the pressure in the tank versus the pressure in the atmosphere. So a pressure gauge would just read negative 0.196 kPa. All right, so next to find the equivalent vertical height for this inclined tube manometer, It's just simple trigonometry. If we set up that we were given a 15-degree angle for the slope, and we have a 40 centimeter long hypotenuse, and that 40 centimeters is along the length of the incline manometer where you actually have your lines to make your reading, then you find that h is about 10 centimeters, which gives this incline to manometer a scale of 4:1, that is 40 centimeters versus 10 centimeters, meaning that each measurement line that your human eye has to read between to get an accurate reading on this manometer is going to be 4 times further apart. So your reading is going to be 4 times more accurate, or your error will be 4 times smaller. And 4 times more accurate readings might make an important difference. So I made this sketch to show the part that students almost always forget about this problem is that the water level in the tank will decrease. So it's super common for students to just find the change in height over on the manometer side, plug that into manometer equation, and call themselves done, right? But there's one volume of water here. As the manometer gets taller, the tank gets lower. Now, if the tank is huge and the manometer is very small, then this lowering might not be relevant, but you have to calculate it just in case. So we've got one skinny cylinder of water on the incline manometer side, 2 centimeters in diameter, 40 centimeters tall, and then one big fat cylinder, 20 centimeters in diameter, that we don't know what the change in level is going to be. That's what we're solving for. But we know that the volumes are the same, and we get that the change in height is 0.004 meters or 4 millimeters. And if we consider the two diameters, we went from a skinny diameter of 2 centimeters to a fat diameter of 20 centimeters. That's 10 times larger diameter. But area of a circle is based on diameter squared. So that 10 times difference gets squared to a 100 times difference. And so since the volume just scales linearly with height, that 100 times different carries forward into the change in height also, which is why this change in height is 100 times smaller. So if you ignored this value, your final answer would probably be off by about 1%. So a lot of times that probably would be negligible, but again, you have to do it just in case. To use manometer equation, we're going to need this final height difference between the two. So from the tank level to the manometer level, it was initially down by 0.02 meters, but then the manometer level went up by about 0.1 meters, and the tank level went down 0.004 meters. So we get a final difference that now the manometer level will actually be above the tank's level, which means that the tank now is probably going to be above atmospheric pressure. If we consider the sort of tug of war between the atmospheric pressure and the tank pressure, initially the tank was losing since the tank level was higher. Atmospheric pressure was pushing in on it. Now, since the manometer level is higher, the tank pressure is pushing against the atmosphere to push it up against the manometer. So the rho GH term by itself gives us gauge pressure plus 0.78 kPa gauge, where gauge pressure is just how much above atmospheric pressure the tank is. And if you add gauge pressure to atmospheric pressure, you get to the final pressure of 102.1 kPa absolute pressure in the tank. Final mystery goal, I teased at the beginning, how to pronounce the word manometer, and it's manometer. It's not manometer. If you call it a manometer, you'll get a couple of chuckles because it's so funny sounding, but then behind your back, some people might start to poke fun at you. And those people might be your professors. So, manometer, not manometer.